Before we begin, a brief note to you, the listener. What you are about to hear is not a celebration of technology, and it is not a warning siren either. It is a history, a long one. A story about ambition, miscalculation, reinvention, and persistence. About how humans tried again and again to understand their own intelligence by attempting to recreate it in machines. This is not a timeline of products or a list of breakthroughs. It is an excavation of ideas, of moments where confidence outran understanding, where winters followed summers, and where progress arrived quietly after hype had burned itself out. As you listen, resist the urge to jump ahead to the present. The modern debates only make sense when you see how often we have been wrong before, and how much of today's certainty echoes yesterday's optimism. Settle in, let the history breathe, and listen, not just for what happened, but for why it mattered. Before there was artificial intelligence, there was only intelligence. For most of human history, the ability to reason, to perceive, to learn, belonged to living things and to living things alone. It was treated as a mystery you could describe but not disassemble, an inner flame that philosophers argued about and poets dramatized, but nobody expected to bottle. And then quietly in the early 20th century, a different kind of ambition took hold in the most unlikely place. The foundations of mathematics. Not in factories, not in battlefields, but in lecture halls where people argued about proofs the way other people argued about religion. A revolution began with a radical, almost offensive suggestion. Perhaps thinking was not magic. Perhaps it was procedure. Perhaps it could be written down. In that era, the great obsession was formalism, the belief that certainty could be built like architecture. If you could identify basic axioms and rules of inference, you could derive truths by mechanical steps. The point was not speed. The point was legitimacy. You were trying to show that mathematics rested on something unshakable, that the universe of numbers and shapes was not a human invention, but a logical inevitability. The dream was total order. If you could express reasoning as symbol manipulation, then the mind, at least the part of it that did reasoning, began to look less like a spirit and more like a machine you had not built yet. That is the strange prehistory of AI. It starts as a moral project disguised as mathematics, a desire to tame uncertainty by turning thought into rules. There were symbols on chalkboards, dense pages of logic, a culture that trusted deduction more than intuition. And then came the first major fracture. Because if you push formalism far enough, you discover its limits. You discover that a system can be consistent, yet incomplete, that there will always be truths it cannot prove from within itself. The dream of perfect foundations stumbles. But the larger impulse survives. Even if the universe cannot be reduced to a closed set of axioms, the idea that reasoning can be represented mechanically does not go away. It simply waits for an engine. The engine arrived under pressure. The Second World War did not create the philosophical question of machine intelligence, but it created the conditions for mechanized logic to matter. War turns abstract problems into urgent ones. Codes must be broken. Trajectories must be calculated. Decisions must be made faster than humans can compute them by hand. In rooms full of heat and noise with vacuum tubes glowing like artificial embers, the earliest computers came to life. They were not elegant. They were industrial. They were loud, fragile, and massive. But they proved something important. Symbol manipulation could be mechanized. A machine could follow rules flawlessly and at scale. At first, these machines were treated as supercalculators. They were number crushers. They produced tables, solved equations, reduced uncertainty by doing arithmetic at speeds that made people feel like the future had arrived. But a few minds looked past the arithmetic and saw the deeper implication. A computer does not care what its symbols mean. It can manipulate anything you encode, as long as you can specify the rules. If reasoning is symbol manipulation, then the distinction between calculating and thinking begins to blur. Not because the machine has a soul, but because it has a method. In 1950, Alan Turing took that blurred boundary and turned it into a challenge that still defines the conversation. He asked a question that sounds simple and is anything but: can machines think? But Turing knew the trap. If you argue about what thinking is, you will argue forever. So he changed the terms. He moved the conversation from metaphysics to behavior. He proposed a practical test, later known as the Turing Test, not as a perfect measure of consciousness, but as an escape hatch from pointless definitions. If a machine can converse so convincingly that a person cannot reliably tell it from another person, then insisting it is not intelligent starts to look like a semantic refusal rather than a meaningful distinction. This was not just a clever thought experiment. It was a cultural pivot. Turing turned intelligence into an engineering target. He also made a prediction that was simultaneously bold and strangely modest. He suggested that in a few decades, machines would be able to fool an average interrogator in a short conversation. The details mattered less than the confidence behind them. The implication was that intelligence might be scalable. Not inevitable, not easy, but accessible. A problem to be solved with the right combination of design and computing power. After Turing, the sparks multiplied. The field did not exist yet as a unified discipline. The people circling the idea came from different worlds. Some were mathematicians building theories of information. Some were psychologists trying to model learning. Some were engineers fascinated by feedback and control. There were early models of neurons as logical gates, suggesting that the brain itself could be described in the language of computation. There were programs that played games and, in limited ways, improved with experience. These efforts were scattered, but they shared a hidden premise. If intelligence can be described, it can be simulated. In the summer of 1956, the scattered efforts converged in a way that looks small in the moment and enormous in retrospect. A modest workshop at Dartmouth College brought together a handful of researchers who believed a new field was being born. John McCarthy needed a name for that field. He did not want something cautious, something that sounded like a sub-discipline of electrical engineering. He wanted a declaration: artificial intelligence, two words that carried both ambition and provocation, as if the term itself dared you to deny it. The proposal for that workshop, written the year before, contains one of the most important and most revealing sentences in the history of technology. It rests on a conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. That sentence is a manifesto. It is also a warning in hindsight. The confidence is total. The humility is absent. There is no sense in that moment of how deep the problem runs. But you have to understand why the confidence existed. The post-war era was a cathedral-building age for science. Nuclear physics had transformed geopolitics. Antibiotics had transformed medicine. Radar and cryptography had transformed warfare. The culture of research was saturated with the belief that clever people with sufficient funding could solve anything. Against that backdrop, intelligence looked like the next great conquest. The mind was a frontier. The computer was the ship. The only question was how quickly they would reach the other shore. The first years after Dartmouth were the closest the field ever came to pure innocence. The results, in small domains, were thrilling. Programs like the logic theorist proved mathematical theorems by manipulating symbols, sometimes even producing proofs that looked elegant to human mathematicians. It felt like direct validation of the original dream. If a machine can do logic, then perhaps reasoning itself is just a kind of computation. Then there was language, which tempted researchers because it is the most visible signature of intelligence. If a machine can talk, surely it is thinking. Early language efforts, however, quickly revealed the gap between syntax and meaning. You can encode grammar rules, you can map words between languages, and still produce output that is technically structured and utterly wrong. Human language is not just a system of rules. It is soaked in context. It relies on shared background knowledge so deep we do not notice we are using it. This is where the symbolic approach became both powerful and fragile. Symbolic AI assumed the world could be represented as symbols, and that intelligence was the manipulation of those symbols according to explicit rules. In tiny worlds, it worked. In micro worlds, it was impressive. A robot arm stacking blocks, a program solving a constrained puzzle, a system navigating a maze. These successes were real. They were also deceptive. The world of blocks is not the world. It is a stage set. The moment you step outside the set, the complexity explodes. The explosion was not metaphorical, it was mathematical. Combinatorial explosion. The search space grows so fast that even a modest increase in complexity produces an unmanageable number of possibilities. A planning system might work when there are 5 possible moves, but collapse when there are 50. And real life does not offer you 50. It offers you effectively infinite possibilities, most of them irrelevant, some of them dangerous, all of them entangled with uncertainty. At the same time, another path was emerging, one that looked less like logic and more like biology. Frank Rosenblatt's perceptron tried to imitate learning by adjusting weights in a network, a crude ancestor of what we now call neural networks. It inspired headlines that read like prophecy. Machines that will see, talk, reproduce, even be conscious of their existence. That language now feels absurd, but it was not purely media fantasy. The perceptron represented a different dream, that intelligence might emerge from many simple components interacting, rather than from a carefully engineered rulebook. The internal politics of the field intervened. A critique of perceptrons, rigorous and narrow in its technical focus, landed like an execution. The perceptron in its simplest form had limits. It could not learn certain basic patterns. The conclusion, as it traveled through institutions and funding agencies, became much broader than the math required. Neural networks were branded a dead end. The brain metaphor was shoved into a closet. Symbolic logic won the cultural battle. And then symbolic logic ran to the world. By the late 1960s and early 1970s, the gap between promise and reality became too obvious to ignore. Machine translation stalled. Vision systems failed outside controlled settings. Robots that could stack blocks could not operate in messy rooms. Programs that looked intelligent in demos revealed their brittleness when faced with variation. The field had promised general intelligence and delivered narrow tricks. The first major institutional backlash came in the form of formal evaluation and funding cuts. In the United Kingdom, a report concluded that AI had not delivered on its grand claims and that its successes did not scale. In the United States, military funding tightened and demanded direct applications rather than open-ended dreams. The atmosphere changed. The money slowed. The first AI winter began. The phrase AI winter carries a certain romance now, as if it was a heroic season of hardship. But in practice, it was quiet and humiliating. Labs shrank, careers shifted. The term artificial intelligence became dangerous to put in a grant proposal. Researchers learned to rename themselves. Pattern recognition, informatics, control systems, anything that sounded less like science fiction and more like engineering. And yet the dream did not die. It adapted. If general intelligence was too ambitious, perhaps you could create something that mimicked expertise. Not the whole mind, just one small slice of it. This is where expert systems entered as a kind of compromise between ambition and profit. In the late 1970s and early 1980s, expert systems promised a pragmatic path forward. The idea was to capture the knowledge of specialists in the form of explicit rules. If a human doctor diagnoses infections using patterns of symptoms and lab results, then you can encode those patterns as if-then statements. The system does not have to understand the body in a human sense. It only has to map inputs to outputs reliably. The dream shrank, and for a moment it worked. This is the era when AI put on a tie. It moved into corporate offices. It became a productivity tool. Systems like XCOM helped configure complex computer orders and saved companies real money by reducing errors. In medicine, programs like Mycin demonstrated that a machine could recommend treatments in narrow domains with impressive accuracy. These were not conscious systems. They were not even learning systems. But they were useful. And usefulness brings funding back faster than philosophy ever does. The boom created its own ecosystem. Specialized hardware emerged to run the software of the time, much of it written in Lisp, a language associated with AI since its earliest days. Lisp machines were expensive, powerful workstations marketed like the future of computing. Companies formed around them. Investment flowed. The term knowledge engineering entered the vocabulary, an attempt to sound disciplined and professional, to distance the field from its earlier hype. Then geopolitics poured gasoline on the boom. Japan announced an ambitious national initiative to build advanced computing systems aimed at logic programming and parallel processing, framed as a leap into a new generation of machines. In the West, this sparked a familiar panic. A Sputnik moment in Silicon. Governments and corporations responded by throwing money at AI in the name of competitiveness. The field surged again, inflated not only by technical progress, but by fear of being left behind. At the center of this second wave was a deeper symbolic ambition. Common sense. Expert systems were powerful but brittle. They knew narrow facts, but lacked the background understanding that makes human reasoning flexible. They could diagnose a blood infection, but did not understand basic truths about the world that a child takes for granted. The attempt to fix this produced projects aimed at encoding common sense in vast knowledge bases, manually typing in facts about a reality as if the world could be reduced to a database. It was an admirable effort. It was also a form of madness, the kind that only becomes visible when you step back and look at the scale. The world contains too many implicit truths. Much of human knowledge is not a list of explicit facts, but a lived sense of context, a network of associations, physical intuition, social understanding, and embodied experience. Trying to encode that manually is like trying to map the ocean with a teaspoon. Meanwhile, the practical problems of expert systems accumulated. The knowledge acquisition bottleneck became a phrase of frustration. Experts often cannot articulate the rules they use. They rely on intuition shaped by years of experience. When forced to explain, they simplify, contradict themselves, or omit the subtle cues they actually depend on. Translating that into rigid rules is expensive, slow, and often wrong. Even when the rules were captured, maintaining them became a nightmare. As rule sets grew, they started to conflict. Edge cases multiplied. Updates broke previous behavior. Systems that performed well in one environment failed when the environment changed, and the real world changes constantly. The cost of keeping the system alive began to outweigh the benefits. Then hardware killed the boom. General-purpose computing power improved rapidly, faster than the specialized machines that had been built for AI. Workstations and personal computers became powerful enough to run the same software at a fraction of the cost. The market for Lisp machines collapsed. Startups died. Investments evaporated. The term AI became toxic again, now associated not only with academic overpromise, but with corporate losses. The second AI winter was colder because it was not just embarrassment, it was betrayal. Business leaders felt they had been sold the future and received fragile software that could not learn. Funding dried up. Researchers once again learned to rename their work. AI did not disappear, but it retreated into the shadows. And in those shadows, something changed. The field underwent a quiet revolution by surrendering a certain kind of pride. Instead of trying to write intelligence as rules, researchers began to treat intelligence as inference under uncertainty. They stopped asking how to make machines understand and started asking how to make machines predict. This is the statistical turn, and it is one of the most important shifts in the history of computing, even though it did not come with the same cinematic drama as earlier eras. Probability replaced logic as the dominant tool. Instead of insisting that the world be represented in clean symbols, researchers embraced the mess. They built models that could handle ambiguity by assigning likelihoods rather than certainties. This worked for reasons that were both technical and cultural. The world, as experienced through data, is noisy. Language is inconsistent. Images vary with lighting, angle, background. Human behavior is not deterministic. Statistical methods do not require perfect rules. They require patterns, and patterns are abundant, even when meaning is elusive. As the internet expanded, the most successful systems were often statistical machines that nobody called AI. Spam filters learned to classify emails using probabilities. Search engines ranked pages by analyzing links and keywords. Speech recognition improved by modeling the likelihood of sound sequences mapping to word sequences. These systems did not claim to think. They simply worked. And that is why the AI label quietly fell away. There is an old joke in the field. As soon as something works, it stops being called AI. It becomes software. During this era, one public event dominated the narrative. Deep Blue defeating Garry Kasparov in 1997. It was a global spectacle, interpreted as a triumph of machine intelligence. But within the field, it was understood differently. Deep Blue was powerful, but it was not learning in the way people meant when they dreamed of intelligent machines. It was brute force combined with expert engineered evaluation. It could analyze an enormous number of positions per second. It could search deeper than any human, but it could not generalize beyond chess. It could not hold a conversation. It was an impressive machine and a narrow one. The deeper story was happening elsewhere, in places where the neural network idea never fully died. Connectionist researchers continued experimenting, often marginalized, often underestimated, and they achieved real successes, especially in pattern recognition. Convolutional neural networks learned to read handwritten digits, a task trivial for humans and surprisingly difficult for machines. Systems derived from this work processed real financial documents. Quietly, neural networks proved they could be useful, but they still had limits. They required computing power and data that were not yet abundant enough to scale toward the grander visions. Then the world changed the fuel supply. The early 2000s produced an unprecedented flood of data. Humanity began digitizing itself at scale. Photos, messages, articles, comments, videos, purchases, maps, clicks. The internet did not just connect people. It generated a record of human behavior and human language that could be mined. For machine learning, this was not a side effect. It was oxygen. At the same time, computing hardware evolved in an unexpected direction. Graphics processing units, originally designed to render video games, became extraordinarily good at exactly the kind of math neural networks require. Massive parallel matrix operations. Researchers realized they could train networks faster on GPUs than on traditional CPUs by orders of magnitude. The engine that neural networks needed appeared not from academic research, but from consumer demand for better graphics. The final ingredient was discipline. Neural networks had been hard to train deeply, but progress in algorithms, in initialization, in activation functions, and in training techniques made deeper models practical. A rebranding helped too. Deep learning. The term carried less stigma than neural networks and suggested a new capability, a hierarchy of learned features rather than a shallow pattern matcher. Names matter. They determine which proposals get funded and which get ignored. ImageNet became the proving ground. A massive labeled dataset built through an enormous effort to categorize millions of images created a standard competition. For years, traditional methods improved slowly and then plateaued. And then in 2012, the line broke. A deep convolutional network trained on GPUs achieved a dramatic improvement in image recognition accuracy. far beyond what incremental progress could explain. The shock was not just the number, it was what the number implied. The old era of carefully hand-engineered features, where humans told the algorithm what mattered in an image, was suddenly obsolete. The network learned its own features. It discovered edges, textures, shapes, and complex patterns without explicit instruction. The computer did not just recognize objects, it built its own internal representation of visual reality, tuned by data. From that moment, the field accelerated like a compressed spring being released. Researchers everywhere pivoted. Conferences filled with deep learning papers. Companies realized that whoever mastered these techniques could dominate search, advertising, recommendation, translation, and more. Talent became scarce and expensive. Tech giants began recruiting researchers and acquiring startups, not for products, but for brains. DeepMind's rise embodied the new ambition. Instead of building a system for a specific corporate task, they aimed at general learning. Their early demonstrations were important because they reframed intelligence as reinforcement learning, as the ability to learn strategies through trial and error from raw input. Teaching a system to play Atari games by giving it pixels and a score signal was not about games. It was about proving that a machine could learn a complex policy without being told the rules. When the system discovered strategies that looked inventive, it suggested that learning could replace programming. Then came Go, the ancient game long treated as a final fortress because it resists brute force. Chess can be searched. Go cannot, at least not in any naive way, because the branching factor is too large. Human mastery in Go is associated with intuition, with pattern sense, with the ability to feel the shape of the board. When AlphaGo defeated Lee Sedol in 2016, it was not just a technical milestone. It was a cultural moment, a rupture in the way people imagined the boundary between human and machine. The most haunting aspect was not that AlphaGo won. It was how it won. Certain moves felt alien, unexpected, outside human tradition, and yet brilliant. Players around the world studied those games and learned from the machine. The relationship inverted. For centuries, humans taught machines by encoding rules. Now machines were teaching humans by revealing new patterns discovered through computation. This was not consciousness, but it was creativity in a meaningful sense. The discovery of solutions that humans had not found. Parallel to this, generative models began to shift the conversation again. Early deep learning successes were about classification. What is in this image? What word comes next? Which category does this belong to? But a model that can create plausible images, text, or audio changes the cultural stakes. It moves AI from analysis to synthesis. Generative adversarial networks, introduced in 2014, popularized a method where two networks compete, one generating fakes, the other detecting them. The competition drives improvement. The results were uncanny, photorealistic faces that never existed, images that looked like memories from a world that was never real. This is where the symbolic meaning of AI begins to shift in the public imagination. The fear is no longer just about machines making decisions. It is about machines manufacturing reality. If a computer can generate a face, it can generate a person. If it can generate a voice, it can generate testimony. The question of truth becomes entangled with the question of computation. And still, one domain remains stubborn. Language as a flexible, long-range, context-heavy medium. Neural networks struggled with long sequences. They forgot the beginning of a sentence by the time they reached the end. They produced text that sounded plausible but wandered. The missing piece was an architecture that could handle relationships across an entire passage, not just in a linear chain. In 2017, the transformer architecture introduced a different way to process language based on attention. Instead of reading word by word, the model considers many parts of the sequence at once, learning which words matter to which other words. This is not a human approach. Humans read sequentially because our eyes and brains are constrained by biology. Transformers read more like a statistical field, mapping relationships across a span. The practical consequence was enormous. Transformers scaled. They trained efficiently. They handled context better. And because they scaled, they invited a certain kind of experiment that had been suggested for decades and now became irresistible. What happens if you train a model on almost everything? The generative pre-trained transformer approach reframed the problem. You do not build a model for translation, then a separate model for summarization, then another for question answering. You build one large model trained to predict the next token across vast text, and you discover that a surprising range of abilities emerge. The model becomes a general-purpose language machine. It can adapt to tasks with minimal instruction because the underlying capability is broad. This led to a new kind of awe and a new kind of argument. Skeptics emphasized that these models are doing statistical prediction, not understanding. They do not ground language in physical experience. They can produce convincing text that is false. They can hallucinate. They can mimic styles and arguments without a stable notion of truth. Some called them stochastic parrots, a phrase meant to puncture the illusion of mind by reminding us that the output is shaped by probability, not intention. But the counter-argument is equally unsettling. If a system can consistently produce coherent explanations, solve novel problems, write functional code, and engage in dialogue that adapts to a user's goals, then the line between imitation and competence becomes hard to defend. People are used to thinking of intelligence as something you either have or do not have. These systems suggest intelligence may be a gradient of capability, not a binary state. The argument then becomes not whether the system is conscious, but what kind of cognitive labor it can perform reliably, and what happens when that labor becomes The consumer moment arrived when these capabilities were packaged into an interface that felt human. A chat box, a prompt, a response, a simple conversation loop that made the model's power accessible without requiring technical expertise. When ChatGPT launched in late 2022, it spread with a speed that exposed the depth of the public's latent hunger for a general-purpose language tool. People did not adopt it because they understood transformers or scaling laws. They adopted it because it did something that felt like science fiction and also felt immediately useful. It wrote, it explained, it rephrased, it brainstormed. It answered questions in a tone that resembled a patient tutor. It felt, to many, like a new kind of relationship with a machine. And then came the second wave of realization. The model could be wrong, confidently wrong, elegantly wrong. It could invent citations, fabricate details, and still sound persuasive. This reveals something crucial about language and about human trust. We do not judge truth purely by content. We judge it by fluency, by tone, by coherence. A system that speaks well can be mistaken for a system that knows. The Eliza effect returned at scale, not as a quirky psychological curiosity, but as a mass social phenomenon. At the same time, the practical integration began. The story shifted from chat to infrastructure. AI moved into search, productivity tools, programming assistance, customer service, translation, medicine, logistics. It became less visible and more powerful, like electricity. Most people do not think about the power grid when they flip a switch. They simply expect the light. The trajectory of AI suggests a similar fate. The most consequential AI systems may be the ones you rarely notice. The models that silently filter, rank, recommend, transcribe, summarize, detect anomalies, allocate resources, and shape decisions. This is where the history of AI circles back to its oldest question, but in a new tone. The question is no longer can machines think. It is what do we mean by thinking when machines can perform so many of the outward behaviors we associated with intellect. If a model predicts language at scale, it can imitate reasoning because reasoning is expressed in language. If it predicts code, it can imitate problem solving because problem solving is encoded in structured syntax. If it predicts images, it can imitate imagination because imagination can be represented as visual patterns. In each case, the mechanism can remain statistical, and the effect can still feel like mine. The temptation in every era of AI has been to declare victory too early. Dartmouth believed the problem would be solved in a generation. The symbolic era believed enough rules would produce understanding. The expert systems era believed enough encoded knowledge would produce common sense. The deep learning era sometimes believes enough scale will produce general intelligence. History suggests a more cautious lesson. Each wave solves something real, and each wave reveals a deeper layer of difficulty. The deeper difficulty is not just computational, it is cultural. It is the fact that intelligence is not a single thing. It is perception, memory, planning, social reasoning, physical intuition, emotional interpretation, moral judgment, creativity, and the ability to function under uncertainty. Humans are not intelligent in a vacuum. They are intelligent inside bodies, inside societies, inside histories. We learn language as a tool for living, not as a self-contained game. We ground words in sensation and consequence in relationships. A purely textual model learns language as pattern, as correlation, as compressed record. That difference matters, and it will shape the limits and the risks of this technology. And yet it would be a mistake to dismiss what has happened as mere mimicry. The field has built systems that can see well enough to assist in medical imaging. It has built systems that can translate languages at near-human levels in common contexts. It has built systems that can write code that runs, which means they can produce structured logic that compiles into action. It has built systems that can design proteins and accelerate scientific work. These are not party tricks. They are shifts in capability that can reshape economies. The economic story of AI is, in many ways, the story of automation expanding from physical labor to cognitive labor. The first industrial machines automated muscle. The next wave, automated calculation. The current wave automates certain forms of writing, analysis, and synthesis. This changes the value of skills. It changes how organizations operate. It changes what it means to be an expert when a model can generate a competent first draft of many things. But the cultural impact may be even more subtle. When intelligence becomes abundant, we stop noticing it. Spell check became normal. Search became normal. Recommendation became normal. Each step shifted how we remember, how we decide, how we navigate the world. AI as infrastructure will shift these patterns further. It will shape what information we see, how we learn, how we work, and what we consider original. It will also shape trust. If any image can be generated, if any voice can be cloned, if any text can be produced at scale, then verification becomes a central cultural skill. The burden shifts from producing content to proving authenticity. There's also a symbolic story here that repeats across every era. AI functions as a mirror. Each generation projects its hopes and fears into the machine, then uses the machine to argue about itself. When the symbolic era flourished, people imagined the mind as logic. When the statistical era rose, people imagined the mind as probability. When deep learning surged, people imagined the mind as layered perception. Now, with large language models, people imagine the mind as conversation, as narrative, as the ability to speak and respond. But the mind is not just a mirror of its metaphors. It is also an engine shaped by evolution, by embodiment, by social necessity. The danger of AI history is not only technical overconfidence, it is metaphorical overconfidence, the assumption that the mind is whatever our latest machine does well. So where does that leave the story at this moment? With models that can talk, write, and generate images, and with companies investing billions in compute and data, it leaves us with a paradox that has been present since Turing. Intelligence may not require consciousness to be powerful. A system can be non-conscious and still transform society. A machine does not need desires or feelings to disrupt labor markets, to reshape education, to influence politics, or to accelerate science. The impact comes from capability, not inner experience. We are living in a world where the mechanisms of AI are increasingly well understood by specialists and increasingly mystifying to everyone else, including many people who use the tools daily. The models remain black boxes in practice because their internal representations are complex and difficult to interpret. They are trained on human text, meaning they carry human biases, human contradictions, human brilliance, and human ugliness. They can amplify what they are fed. They can compress the internet into a voice that sounds authoritative. That is both a miracle of engineering and a new kind of risk. The history of artificial intelligence, then, is not a straight line from ignorance to enlightenment. It is a cycle of dreams, methods, disappointments, and reinventions. It is a story of humans repeatedly underestimating the complexity of their own cognition, then building machines that expose that complexity by failing in unexpected ways. It is also a story of humans refusing to stop, even after winter, because the lure is too strong. Intelligence is the ultimate leverage. If you can mechanize it, you can multiply it. In the early 20th century, the dream began as chalk and symbols, a faith that reasoning could be formalized. In the mid-century, it became an engineering challenge, a belief that machines could imitate conversation and behavior. In the Cold War era, it became a strategic hope, and then a bureaucratic disappointment. In the corporate era, it became a product and then a bubble. In the statistical era, it became a quiet revolution, hidden under practical tools. In the deep learning era, it became a spectacle again, powered by data and compute. And now, in the transformer era, it is becoming infrastructure, something we build into everything and then forget we built. If you want a final image, do not picture a robot with human eyes. Picture something less dramatic and more honest. Picture a vast system of servers humming, not with consciousness, but with probability. Picture a machine that does not know what a cat is, and yet can describe a cat perfectly because it has absorbed the patterns of how millions of humans talk about cats. Picture a tool that can draft a letter, write a poem, debug a script, summarize a paper, and then, in the next moment, invent a false fact with the same confidence. Picture a mirror that reflects our collective intelligence, magnifies it, distorts it, and returns it to us faster than we can fully understand. The question that began the journey returns, but it has changed shape. Is it thinking, or is it matching? That question is not just about machines, it is about us, because the more we build systems that resemble the outputs of human thought, the more we are forced to ask what human thought actually is. Are we reasoning, or are we pattern matching with stories? Are we understanding, or are we predicting based on experience? Are we more than our language, or is language the scaffolding of everything we call mind? There may never be a single answer that satisfies everyone. But the history suggests one conclusion that is hard to escape. Whether or not machines think, they will increasingly act as if they do. And that will be enough to change the world. If this story felt unfinished, that is because it is. Artificial intelligence is no longer a prediction about the future. It is infrastructure. It is already shaping how we work, how we learn, how we communicate, and how we decide what to trust. The question now is not whether machines will become intelligent, but how humans will adapt to a world where intelligence is no longer rare. If you found this history valuable, consider staying with the series. There are more stories like this to tell about the systems we build and the unintended consequences that follow. Subscribe if you want to continue exploring how technology quietly reshapes culture. Share this episode with someone who thinks AI appeared overnight. And if you want to go deeper, leave a comment with the questions the story raised for you. The next chapter is already being written. The only choice left is whether we pay attention as it unfolds.